Mm. So today I want us to take a look at chemical equilibrium, right? But before you know what is chemical equilibrium, you have to know the difference between an open system, right, and a closed system. Are we together? So I will make an example of an open system. Let's say you have a beaker, ne? And this beaker, you have a fire here. You've put it this beaker with the fire. This is fire. This is fire. Do you get it? So, and you have your water here, right? You have water, we have water, we have water, you have water. Yeah, man. Ish. Sure. Yeah, ngizwa. Sure, tiskipani. Ngibambele kancane. So, yeah. Yeah, guys. Are we still there?
Yes, sir.
Okay. So, here's the beaker there, ne? Here's the beaker. And you can see that this beaker, it doesn't have a lid, right? And we have another beaker here. Okay, let me do this. But this one, this time around, it has a lid. It is closed, this one. And we still have water inside the beaker. Ne? And with the fire, right? If I may ask, ne, we can see that we have the system and water inside the beaker, which is boiling. So after some time, what's going to happen to this water? What's going to happen?
It's going to evaporate, sir.
Yes, it's going to escape, right? To the environment, right? So would you say there's like this type of a reaction, it is reversible? Hmm? Would you say that this type of a reaction is reversible?
No, sir.
Why? Why is it not reversible?
Because I get when you bring like water to a boil, it turns into a gas, and then that gas is going to escape into the surroundings. It doesn't have like any lid to hit the lid and like condense it back into water, back into the beaker. I don't know if that makes sense. Cause like
So in other words, the closed system is reversible.
yes,
Why would you say that?
because the gas produced by water won't have anywhere to escape. It's just going to hit the lid of the roof and then condense it back into water. Like
Yes. Basically,
yes,
you're going to have H2O liquid, ne? Wait. Mm, okay. So it's going to be H2O in a liquid phase, changing into H2O in a gaseous phase, right? It's going to change from liquid to gas and gas to liquid. Are we together? Liquid to gas, gas to liquid, liquid to gas, gas to liquid. But as for this one, there's going to be H2O from liquid to gas, right? This is the one-way reaction, right? Like it changes from liquid to gas, and but that the gas it cannot change back to liquid because of the gas is escaping the container. We understand each other, right?
yes,
The gas is escaping the container. So this type of a system we call it an open system. Just like whenever you are producing something, let's say for instance a combustion reaction. Let's say you have CH4 plus O2. Obviously, you're going to form H2O plus CO2, right? Perhaps 2 here. And 2 plus 2 is 4. And you're going to have 2 here. So perhaps this reaction, do you see this carbon dioxide? It is escaping the container. Do you get that? It means that this reaction occurs on an open system because of why? The gas is escaping the container, and that reaction it is only one way, right? But there are some reactions which are reversible. You get what I'm trying to say? If you compare reaction rates and chemical equilibrium, reaction rates only occurs on open systems because of they have to measure how much gas is released from the reactions that is occurring. You get that? And in chemical equilibrium, we measure, obviously, we are going to measure how reactant tends to products and products tends to reactant. You get what I'm trying to say? Are we together, guys?
yes,
So this is the flow chart, guys. Ne? This is the flow chart of chemical equilibrium. Basically, we have to learn everything that is here, right? But you shouldn't stress about that. We are going to learn about how the catalyst affects the equilibrium. Obviously, you have to learn about the factors that affects the chemical equilibrium. Same as the factors that affects the reaction rates. We have to learn about the factors that affects the chemical equilibrium. And we have to understand that that the reaction has to be reversible. Remember, the conditions of equilibrium, guys, just like the conditions of reaction rates. Right? These two, they're using the same style, but different types of condition. Obviously, whenever you have this, ne? In chemical equilibrium, in chemical react, chemi-ish, chemical equilibrium, ne? In chemical equilibrium, the requirements means of this type of the reaction, guys. You have to understand that the reaction has to be reversible. Ne? And number two, the reaction must be in a closed system. We understand each other. The reaction must be reversible and the reaction must be in the closed system. And you should understand that they are same as the factors that affects the reaction rates, they are the factors that affects the chemical equilibrium. And you have to know how to define the dynamic, right? The dynamic equilibrium. Ish. Man. Dynamic equilibrium. Right? Dynamic equilibrium. What is a dynamic equilibrium? You have to know how to define the dynamic equilibrium. So what is a dynamic equilibrium? Obviously, it is the rate of the forward reaction equals to the rate of the the reverse reaction. It means for the amount of the products. Pella, remember, guys, remember the reaction is like something like this. If we have A plus BC, you are going to receive what? A, B plus C, right? This is the forward reaction. This is the forward reaction. Ne? This is the forward. This is the backwards. Right? This is the reverse reaction. Right? That is the forward reaction. That is a reverse reaction. The amount of the products is going to be equals to the amount of the reactant. Maybe this reaction, it forms 20 kg of the products, or maybe 20 moles, or the concentration of 20 moles per dm3 on the products. It's going to form, even the reverse reaction will behave the same way as the products, as the forward reaction. Are we together? If the forward reaction produces 20 kg, for instance, it means already the reverse reaction will produce the same amount as the forward reaction produced. Do you understand, guys, so far?
Yes, sir.
You get it? So it means already the time it will take, and at the same time, the time it will take for a forward reaction to occur. You get it? Because of when we talk about the forward reaction, we when we talk about the forward reaction, we are talking about reactants. Let's see. When we talk about the forward reaction, we we are talking about forward reaction. We are talking about reactants. Ish. We are talking about reactants turning back, turning into products, not turning back into reactants turning into products, into products, right? That's the forward reaction. That's where AB becomes AB plus C, right? That's the forward reaction. So the reverse reaction, it's when products turns back into reactants, right? It's when the product turns back into reactants. So in other words, in order for you to see, guys, in order for you to see that the reaction has reached equilibrium, how will you see that? You will see by what? How will you see that the reaction has reached equilibrium? You will see by the rate of forward, ne? The rate of forward reaction, the rate of forward reaction, the time it takes for forward reaction to occur. And remember, what is the forward reaction? The time it takes for the reactants to turn into products, right? The time it takes for the reactants, these are the reactants, turning into products, which is the forward reaction, the rate of forward reaction being equal to the rate of the why did it change the reverse reaction. It's when the rate of forward reaction is equals to the rate of the reverse reaction. So if the time it takes for the reactants to turn into products is equals to the time it takes for the products to turn back into the reactants. For example, if we have H2 plus O2 is going to be equals to H2O, right? And if I were to balance the equation, I'll just put 2 here and put 2 there. So the time it takes for the hydrogen to combine with oxygen, which they both form water, if this time it is equals to the time it takes for water to break into hydrogen and oxygen, it means that's where we can confirm that the reaction it is at its equilibrium space or equilibrium phase. Guys, do you hear me? But langutla mar.
Yes, sir.
Yes. Because I need you to understand this first part, and understand hore, what is chemical equilibrium about. Because of if you check here, they are telling you that the dynamic equilibrium, it is the rate of forward reaction being equals to the rate of the reverse reaction. The rate of forward reaction being equals to the rate of the reverse reaction. And you can see here they further emphasize to you that they said the amount of reactants, right? And the amount of products will remain constant. It means that the amount of the reactants that you are going to obtain is going to be equals to the amount of products that you are going to obtain. That's where you would say that the system is at equilibrium, right? So that's what you have to understand about chemical equilibrium. It's all about that, right? It's all about that. It's all about reversible reactions and closed system, and what are the factors that you would use when the system is at equilibrium. But for now, we are going to talk about the factors that affects the chemical equilibrium. We are not going to talk about the equilibrium disturbance. For now, we are going to talk about the factors that affects the chemical equilibrium. So, if we check, if we check the graph before, if we check the graph, you will have a graph like this, right? You'll have a graph like this. Yes. Mm, right? So, in this graph, it starts from 0, and your x-axis, it represents the time, and your y-axis, it can represent it depends. The graph can represent the mass loss, or it can represent the amount of volume that is escaping the container. Are we together? It can represent the amount of the volume that is used to represent to escape the container. That's what you need to know, right? Because of now, you have to remember, that I want you to keep in mind, before other things, I want you to keep in mind that I want you to keep in mind that uh, equilibrium is all about the rate of forward reaction equals to the rate of the reverse reaction. You get it? And this AB, or A plus BC, is going to be equals to AB plus C, is going to be the forward reaction. And we have the reaction, or like we have the reverse reaction, which is fine. And now I want to represent this on the graph, right? This side, it can represent the volume that is lost, right? You can have your volume that is lost, maybe the volume of the gas in decimeter cubed that is lost, right? And obviously on your x-axis, the change in time is the one that is going to be represented, which is fine, right? So guys, are you still with me?
Yes, sir.
Yes.
Yes, sir.
Yes. So check this out, guys. Sometimes this is going to be your initial volume, right? It's gonna be your initial volume. Maybe you started your reaction having some amount of the volume, right? Or maybe let me just let me just use like let me just use mass loss, ne? Let me just use mass loss. Ne? Let me just use mass loss or yeah, mass loss. Let me just say mass, ne? Mass in grams, right? Maybe they would say the mass of whatever, like let's say the mass of a certain substance. So maybe you have, because obviously, or maybe I would just use the very same reaction of AB plus C is gonna be equals to what? A a AC plus B, depending, right? Depending. You get it? And if you check your graph very well, maybe you can check, you can measure, you can have your graph for reaction rates, maybe the mass loss versus the time, ne? And you can say this is the mass of AB. Because remember, guys, when the mass of the reactant goes down, the mass of the products will go up, right? If the mass of AB goes down, the mass of the reactants will go up. So let's say here you are measuring your reaction rates, obviously, using the graph. And this, obviously, is going to be the mass of the reactants. Ne? Obviously, it's going to decrease up until it becomes flat like that to show that your graph, to show that your reaction has reached its state of equilibrium. And you should notice something. Because of maybe you started your reaction, maybe let's say you have the mass of the reactants, maybe, or maybe I'm measuring the mass of AB. Initially, it was 10 grams, right? Initially, it was 10 grams. Let's say this is the mass of AB, ne? It was 10 grams, right? And when it was 10 grams like this, as the reaction occurs, ne, the mass goes down. Do you see that? The mass goes down of AB since it's the reactant. And as the mass of AB go down, obviously the graph of the products, because of this graph, it represents the mass of the reactants, right? Going down. So the mass of the products is going to increase because of, you can see here now, as the mass of the reactants decreases, the mass of the products increases. This is the mass of the reactants, right? It is the mass of the reactants, or it is the forward reaction, or the mass of the reactants. And this is the reverse reaction, right? Reaction, which shows you that, like, as the reaction continues, the mass of the reactants goes down and the mass of the products goes up. It means sorry, the reactants they become used, right? This reactant will be used, and when it's used, obviously the mass of AB it will go down. And as the mass of AB goes down, the mass of the products goes up. One good precise. Because of AB, it is used to form AC or is to form B, depending on the conditions of the equilibrium. Are we together? Because of remember, if you check the rate of the forward reaction and the rate of the reverse reaction, they're at what? They're at equilibrium. Because of this is the definition of equilibrium. Do you see that? This is the definition of equilibrium. The rate of forward reaction is going to be equals to the rate of the reverse reaction. And if you check these two graphs, the rate of the forward reaction as it goes down, the rate of the reverse reaction it starts to evolve, right? And whenever they meet each other at this section here, whenever they start and meet each other at that section there, obviously, when the rate of forward reaction it is on top of the rate of the reverse reaction, that's where you can confirm that these two reactions they've reached their state of equilibrium. Are we together?
Yes.
Lanswaro. Yeah. So yeah, you have to understand the graphs, ne? You have to understand the graph. So this it was just an introduction of how the equilibriums looks like on the graph. But I will go back. I will just go back. Don't worry too much for now. Don't worry too much about the graphs, ne? Don't worry too much about the graphs, and let's focus more on the factors that affects the reaction, the chemical equilibrium. Let's focus on the factors that affects the chemical equilibrium, right? So as we can see, ne? As we can see on our screen there, I want us to focus on the factors that affects the chemical equilibrium. Ne? We are going to follow this. We are going to follow this flow chart here and talk about the factors that affects the chemical equilibrium, right? So here, remember, chemical equilibrium it has requirements, guys. The chemical equilibrium it has requirements. The requirements are what? The reaction has to be reversible in a closed system, right? Reversible and closed system. And what is the dynamic equilibrium? The dynamic equilibrium is this one. Basically, I should add and say dynamic. This is dynamic equilibrium. The rate of forward reaction it has to be equals to the rate of the reaction, the reverse reaction. And now I want us to talk about the factors that affects the the chemical equilibrium, right? The factors that affect the chemical equilibrium. Number one, we have to know how the concentration affects the chemical equilibrium, guys. We have to know how does the concentration affect the chemical equilibrium. When you add the concentration, what is happening and how is the graph behaving? You get what I'm trying to say? Number two, we have to talk about the temperature, right? And the type of the reaction that we are having, whether the reaction it is exothermic or endothermic. Endothermic. Ish. So endothermic or Ish. Or exothermic. Yes. And yeah. Number three is gonna be pressure slash volume, right? When you increase the pressure, or when you decrease the volume, or when you expand the volume, or when you increase the, basically here you have to understand the relationship between the pressure and the volume, right? And obviously the catalyst, but the catalyst has no effect, right? The catalyst has no effect in chemical equilibrium, but its job is to do what? Is to speed up the reaction. You get what I'm trying to say? Is to speed up the reaction. These factors, these are the factors that we're going to talk about when it comes to chemical equilibrium. So now, as I can tell here, let's see now. The factors that affects the equilibrium, we have concentration, we have temperature, we have pressure. Catalyst has no effect on chemical equilibrium, right? Like I said to you, you have to understand that catalyst, it has no effect of chemical equilibrium. So we have to know, guys, which reaction it is favored, basically, because of the what do you call this? The aim of chemical equilibrium is to produce products, and is to know whenever you are implementing the factor, maybe you are implementing concentration to affect the equilibrium, which reaction is going to be favored, whether it's the forward reaction or whether it's the reverse reaction. You have to know that. You get what I'm trying to say? For now, it might sound confusing, but when you do it, the application, you will see how it makes sense. But now you have to know that the purpose of the chemical equilibrium is to analyze whether the reaction that is favored is the forward reaction or is the reverse reaction. Are we together? Lanswaramas.
Yes, sir.
So yeah. Now, guys, I want to talk about the factors that affect the chemical equilibrium. Ne? I want to talk about the factors that affect the chemical equilibrium. So, for now, let's talk about the concentration. Ne? Let's talk about the concentration. Number one factor, we are going to talk about the concentration. Ne? How does the concentration affect the chemical equilibrium? Ish, I will make examples, but I'm not sure whether my examples will help you to make sense out of whatever that I'm going to try and implement today. Ungutwisisa? So, So yeah, let's talk about the concentration, guys, ne? Let's talk about the concentration. So when you talk about the concentration, let's say for instance you have firewood, ne? Firewood plus matchbox. What is it that is gonna be produced? If you combine the two, you have firewood and matches. What is it that is going to produce with these two? Or is the question doesn't make sense, guys?
So fire or flame?
Yes, the flame is going to be produced, right? The flame is going to be produced. So I want you to do to check something, ne? With this example. If I add more firewood, I mean, not wood, wood, ne? If you add more firewood, what's going to happen? You're going to have more flame, right? Basically, this is going to be your system, guys, ne? What's going to happen when you add more firewood? The system will use that firewood to produce more flame. Or am I lying?
No, sir.
It's going to use that firewood to produce more flame. So it means that when you increase the amount of firewood on basically the reactants, basically when we bring it to chemical equilibrium, when you increase the concentration of the reactants, the system will use those reactants to produce what? More products. You get it? Are we together?
Yes,
Yes.
sir.
So that's how chemical reaction, like that's how a chemical equilibrium it is influenced because of whenever you add reactants, the system will use that product. For instance, what's going to happen? Ne? Let me bring it to this sense. What's going to happen if maybe I add more H2O in the system? Let's say, for instance, I have H2 plus O2, right? It's going to be equals to H2O. It's going to be 2 here. It's going to be 2 here, right? What's going to happen if I add more of the oxygen? So this system is going to use what? More of this oxygen to produce more water. It means, sorry, the concentration of water, it will increase because of the system will do what? Will do what? Will use the oxygen that is added into the system to produce more water. I'm not sure if I'm making sense there. You get what I'm trying to say?
Yes, sir.
So check this out, guys. Now, this is when we talk about an increase in concentration. Wanhlalwa ke? Wanhlalwa ke? So, what's going to happen now? What is going to happen? Obviously, here you will say, Hori, the system will use that oxygen to form more water, so more products will be produced. And if the system it is using this oxygen, it means that the forward reaction is going to be favored. Do you see that? Because of whenever you add, whenever you increase the amount of oxygen, right? The system will use the amount, will use the oxygen to produce what? To produce H2O. And obviously, whenever the system uses the H2O, what's going to happen? More products will be formed. Or am I lying, guys? Pella, if the system it is using, it's like adding a sweet 8. Do you know what's a sweet 8, right? It's like adding a sweet 8 into water. Obviously, what's going to happen? The system, which is water, will dilute that sweet 8 to produce more juice. But instead, obviously, the amount of the reactants will go down and the amount of the products will go up. Right? So here, more products, which is what? Which is H2O, will be formed, right? More products will be formed. Will be formed, right? More products will be formed. And what's going to happen if more products will be formed? The forward reaction is favored because of if more products will be formed, the forward reaction will be favored, right? The forward reaction will be favored. The forward reaction will be favored when you increase the reaction. Girl. Push. So now, guys, please someone tell me, can you predict what's going to happen if maybe, let's say, some of the H2O will be removed? Let's say this H2O now is going to be removed. Because of here, or maybe O2 is added. Ne? O2 is added. It means the concentration of O2 is added within the system. It means this will happen, right? The system will use O2 to produce H2O, so more products will be formed, and the forward reaction is gonna be favored, right? So what's going to happen to the same reaction? To the same reaction, which is gonna be H2O, to the same reaction when O2 is removed. What's going to happen to this reaction when O2 is removed? And remember, the reaction is reversible, right? And if O2 is removed, what's going to happen? The system will use the products to do what? To form more of that O2. Because of, remember, that's the system. It works to do what? It's replaced what it is left. If more of the H2O it is added, or maybe the O2 it is removed, it means the concentration of the reactant went down, right? But the system will use H2O to form what? To replace that O2. Anger. Because of we also have the reverse reaction, which is H2O, which is equals to H2 plus O2. Now this reaction is gonna be favored, and which is the reversible reaction. Lang understand, Damar? Do you
Yes.
guys understand this concept?
Yes, sir.
Because of why? What's happening? If O2 is removed, if O2 is removed like this H2O, it will do what? It will be used. This H2O, it will be used to replace that O2, right? It means that H2O will be used to form, right? H2O will be used to form the O2. So it means what will happen to the concentration of the products, guys? What's going to happen to the concentration of the product? Will it increase or will it decrease?
Decrease.
Yes, it's gonna decrease. You get it? So the concentration the concentration of product will decrease. Right? And when the concentration of product decrease, which reaction will be favored? If the concentration of product decreases, it means the concentration of the reactants will increase, right? But I don't want to put it that way because of why O2 is removed. So I would just say the concentration of products will decrease. So which reaction is going to be favored? Will the forward reaction be favored since H2O it decreases? Hmm? Because of what will happen? If water it is used to form O2, it means now the reaction it is in that direction. Do you see that?
Yes, sir.
So it means the reverse reaction will be favored. Do you see that? So let's go to our script and see what's going to happen. when we talk about the concentration. So check, ne? They're saying if you increase what? The hydrogen, the forward reaction is favored. Do you see that? Because of why? If you increase this guy over there, you're going to have more of this H2S. Are we together? Because of the system, it will use that hydrogen to form more of hydrogen sulfide or sulfate. Are we together?
Yes, sir.
So this, if we decrease this guy over there, and you have to understand this concept very well, guys. It's a bit tricky, but you have to understand it. So if you decrease this guy over there, if this guy goes down, right? If this guy goes down, what's going to do? What is the system going to do? The system will ensure that the amount that it is taken, I mean, the amount that is taken is going to be replaced. And how is it going to be replaced? The concentration of products, it will be used to replace the space there that is left. You get it? So it means that this H2S is going to be used to form that H2 there. Are we together? So this is the dynamic equilibrium that we are talking about. And that's how the concentration functions in this instant. Right? So this is how you have to understand this thing, guys. This is how you have to understand this. And this is what Le Tetzlaer's principle implies. Because of these factors these are the factors that affects the equilibrium, right? Because of this is how the concentration affects the equilibrium. Are we together?
Yes, sir.
Yes. So now, number 2, we have temperature, ne? We have temperature, ne? Temperature. What's going on with the temperature? What effect does the temperature has on the effective rate, on the reaction rates? Who can tell me? What effect does the temperature have on the reaction rate?
Increases the reaction rate.
Yes, it increases the reaction rate, right? So, if I have A, B plus C, it's going to be equals to AC plus B. Ne? And I'm telling you that the enthalpy is greater than 0. What type of a reaction is that one?
Endothermic.
It's endothermic, ne?
Yes, sir.
So, since we are having an endothermic reaction, what's going to happen? Your first line, you're going to state that because of now, if we increase the temperature, ne? The temperature, and we are having this guy over there, right? This guy implies what? It tells us that the forward reaction, because of the forward reaction is reactants to products, right? This is the forward reaction. It tells us that the forward reaction, it is endothermic. So what about the reverse reaction? Is the reverse reaction endothermic or exothermic?
Exothermic.
Thank you very much. So if the forward reaction, it is endothermic, and the reverse reaction, it is exothermic. The reverse reaction is exothermic. You get it? So let me tell you, number one, the increase all the time, guys, ne? The increase, ne? In temperature favors, I don't know, I'll just say favors the endothermic reaction. You get it? So now, which reaction is going to be favored? Is it the forward reaction or is it the reverse reaction when the temperature it is increased there?
The forward, sir.
The forward reaction is going to be favored, right? So now you're going to state on bullet number 2 and say the forward reaction is favored. Hey, how do we spell favored, guys? Is it V-O-R or is it V-O-E? I'm confused now.
This one
Which
is the
spelling?
South African spelling, sir, so it's correct.
So this one.
Yes, sir. It's the South African version of it.
And what about this one?
It's the American one.
They are both correct.
Yes, so they're both correct.
No, let's be South African, okay? So, all right. So the forward reaction is gonna be favored, right? And what's going to happen to the reaction rate? Because of the temperature is increased. Now we have to talk about what? Since the forward reaction, it is endothermic. Yes. And you have to state that the forward reaction is endothermic. That's very important to show that you see that the forward reaction is endothermic, right? To see that the forward reaction is endothermic. So it's going to be favored and it's endothermic. And it means that more products will be formed, right? So yeah, more products will be formed. So check this out, guys. What if I now decrease the temperature? What if I now decrease the temperature? What's going to happen if I decrease the temperature? What if now I decide to decrease the temperature? What if now I decrease the temperature? What's going to happen? Which reaction is going to be favored?
Reverse reaction.
The reverse reaction.
The reverse reaction, right? Because of why? If we have A plus BC, which is equals to B. Okay, let me just say AC plus B, ne? Plus B. And the enthalpy is greater than zero, right? So remember, now the temperature is decreased. So you'll say what? The decrease Is my decrease correct spelling, guys? Or is it I or is it E at first?
Correct, sir.
Okay. Decrease in temperature favors the what? The exothermic.
So isn't the enthalpy less than 0?
No, no, no. The decrease, check this out. The forward reaction is what here? Is it endothermic or exothermic? The forward reaction.
What is endo, sir?
Forward is endothermic, right?
Yes, sir.
Yes, sir.
Yes. Yes, it means now when you talk about the decrease in temperature, is going to favor what? The exothermic, right?
Yes, I'm asking about that enthalpy. You said enthalpy is greater than 0, so I'm asking about that.
Yes, enthalpy is greater than 0 here.
Okay.
You see it now, or maybe I'm misunderstanding you.
I'm confused because enthalpy is greater than 0, but then the reaction is exothermic.
No,
It
we are
favors
talking about it. Listen, don't be confused. We are talking about
yes,
the
sir.
decrease in temperature. It favors what? The exothermic reaction. So, what is the name? Like, what is the exothermic reaction? Which reaction it is considered to be exothermic?
The reverse reaction.
The reverse reaction. So, you are going to state and say reverse reaction is favored. Is exothermic, I mean. Why one? Then it's gonna be what? The reverse reaction is what? Is favored. Do you see that? Because of in the exam, they won't give you, it's either they gave you the forward reaction being endothermic or the forward reaction being exothermic. You get what I'm trying to say? They can give you the forward reaction being endothermic and they say, oh, the temperature is decreased. Do you get that?
So I think
Do
you
you
misunderstood the question name.
Mm.
She's asking if why you wrote it's endothermic, God, are you explaining an exothermic reaction?
Where did I
Yes.
write where did I write the
It says
endothermic?
enthalpy is greater than 0, so I'm
Enthalpy is
asking,
greater
isn't
than
it like
0.
less than 0?
No, no, you guys, you are misunderstanding me. The forward reaction is what?
Also,
It's
we're
any.
writing the integral, the enthalpy of the forward reaction.
Oh, the decrease. Oh,
Yes,
okay.
yes. The
Okay, so I
forward
got it.
reaction, it is endothermic, but when you explain, what are you going to say? The reverse reaction is exothermic.
Okay,
Okay.
understood, sir. So forward reaction increase and decrease. Okay, got it.
You get it?
Yes, sir.
So the reverse reaction, it is favored. The forward reaction, it is not favored because of the temperature, it is decreased. Do you get it? So this is how you explain it. And what's going to happen to the reaction rate? The reaction rate will increase or it will decrease? Hmm?
Decrease, sir.
Will decrease. Hmm. That's how you explain it. Then, yeah, this is for temperature increase. This is for temperature decrease. This is for temperature increase. And this is for temperature decrease. So Yeah, you should get the difference, guys. Let's see on our script on what is happening. Do you see that? Here, do you see here? How is the enthalpy here? Hmm?
It's
How is
exothermic.
then? Yes, it's exothermic, but whenever they decrease the temperature, what's going to happen? The forward reaction is going to be favored. Do you see that? But whenever they increase the temperature, because of the forward reaction, it is exothermic. It means that the reverse reaction is going to be endothermic. Hence, it's going to be favored. So, do you understand it? Do you understand this concept?
Yes.
Yes. Okay. So, on our next lesson, we are going to talk about the pressure. Yeah. We're going to talk about the pressure. So for now, I'm just going to stop here at temperature, and later on, we're going to continue with reaction rates. So I'm going to talk about the pressure, and yeah, then we move. So for now, any questions? So do you have any questions?
None from me, sir.
Okay. No, I believe there's no question. So if there's no question, you can dismiss, ne?
Thank you, sir.
No
Thank you.
problem. Sharp, no problem.